So, if I threw this ball, how would I know when it reaches its peak height? Imagine a scenario where someone throws a ball to another person and we wanted to figure out when the ball reaches its peak height and what the maximum height the ball reaches actually is. So the height of our ball over time can be modeled by the following quadratic equation, which is h equals 5t minus t squared, where h is our height and t is time. And our equation is true from the very start, 0 seconds, to 5 seconds. Now, the first way we can solve this problem is just algebraically, using our quadratic equation and converting it to turning point form. So there we can find how long the ball takes to reach its maximum height and what it actually is. So the first step we're going to do is, we're going to rewrite our equation so it's a bit nicer by making this quadratic term here positive. So what we're going to do is we're going to rewrite h, but we're going to take out the negative. So it's going to become t squared minus 5t. So now that we have a positive quadratic in there, it'll be a little easier to solve now. And from there, what we're going to do is we need to complete the square to convert it to turning point form. So this is where we're going to take half of our 5, then square it. So half of 5 is 2.5, and then 2.5 squared is 6.25. So we have t squared minus 5t, and this is going to be plus 6.25. Now, we can't just change our equation, right? It has to stay the same. So what we're going to do is we're also going to subtract 6.25 straight after that. And that's our equation so far. Then all we have to do is convert it to turning point form here. And we're going to complete the square. So it'll become t minus 2.5 squared. And then we have our minus 6.25. And then all that's left is to take out the minus. So it's going to be minus 2t minus 2.5 squared, and then minus negative times negative is positive, so plus 6.25. And that's our equation in turning point form. So we can see now that the maximum height that we reach is 6.25 meters, ry, and the time it reaches that height is at 2.5 seconds. So that's the first way that we can solve it. We get that the time it reaches its maximum height is 2.5 seconds, and the height is 6.25 meters. Now, the second way is what we call using differentiation. So differentiation is, put simply, the instantaneous rate of change in something. So in the context of our example, what it's going to be is the instantaneous rate of change in the height of our ball. All right. So using that, what we can do is find when the ball reaches its maximum height, what that instantaneous rate of change is, and then using differentiation, we can solve for when that happens and what the height is. Now, the first thing we have to do is figure out, okay, at the maximum height, what is going to be that instantaneous rate of change? Let's think about it. If we have our parabola here, as we get closer and closer to that maximum height there, it approaches 0. So at that maximum height there, our instantaneous rate of change is actually going to be 0 meters per second. So the way that we represent that is by using fractions. So to denote the instantaneous rate of change, we, instead of writing h over t, we write dh over dt. So at the maximum height, dh over dt equals 0. So now we know what the instantaneous rate of change will be at that maximum height, but we need to find out, first of all, when that happens and what the height will be as a result. And that's where we actually have to differentiate our equation. So there's one basic rule that we're going to use for this. So with differentiation, we're going to differentiate each of our separate terms individually. So our 5t and our minus t squared individually. So we're always going to get an equation dh over dt equals something. And that will give us the instantaneous rate of change in the height of the ball at any given moment. And it will be in terms of t. Now, in order to do that, we have to use a rule, which we call the power rule. So with our power rule, if we have our equation like kt to the power of n, then dh over dt is going to equal knt to the power of n minus 1. Now, k and n are both constants, so they're just numbers. And basically, all we have to do when we're differentiating is figure out what those numbers are and then use that rule to figure out our differentiated terms. So if we differentiate our equation h equals 5t minus t squared, we're going to do that. We're going to do each term separately. So we've got dh over dt equals something. Let's start with the 5t first. We can write 5t as 5t to the power of 1. So we can see now that we have our term in power form, and we just have to find out what our constants are. So by inspection, we can see that k equals 5 and n equals 1. So now we know that the differentiated term is going to be knt to the power of n minus 1. So we just substitute in those values. So k is 5 and n is 1. So we've got 5 times 1 times t to the power of n minus 1. Now n is 1, so it's going to be 1 minus 1, which is 0, right? So we've got 5t to the 0, and remember anything to the power of 0 is just 1. So our first term is just going to be 5. So now we've differentiated our first term, 5t, which is just going to be 5. Let's have a look at the next term, minus t squared. Same thing. We're just going to find out what our constants are and then plug it into our power rule to find out our differentiated term. So by inspection again, we can see that k is minus 1 because we've got the minus t squared, and n is 2. So using our power rule, we've got k, which is minus 1, n is 2, t to the power of n minus 1, which is 2 minus 1. Now minus 1 times 2 is minus 2. And we've got t to the 1. So we have minus 2t as our second term. So our final differentiated equation is dh on dt equals 5 minus 2t. So we know that at any given moment on this parabola that the instantaneous rate in change of our height is going to be 5 minus 2t. So all that's left to do now is find, okay, when does that happen? We know that at the max height, the instantaneous rate of change in the height is going to be 0. So what we can do is just solve for when dh on dt is 0 to get our time when the max height happens. So 0 equals 5 minus 2t. So therefore 2t equals 5, and then t equals 2.5 seconds. So you can see that we get the same solution as earlier, t equals 2.5 seconds. So now that we know that the ball reaches its peak height at 2.5 seconds, what is the maximum height it actually reaches? Unlike our first method where we had to rearrange our equation, all we can do now is just take our time value and substitute it back into our original function. So if we wanted to find out when the max height happens, we know that it happens after 2.5 seconds, and we're just going to substitute it in. So h equals 5t, so 5 times 2.5 minus t squared, which is 2.5 squared. So h equals 5 times 2.5 is 12.5, and 2.5 squared is 6.25. So our height is 12.5 minus 6.25, which is just 6.25. And again, we get the same solution. Our max height is 6.25 meters. So you can see that with our second method, it's a lot shorter, got less steps, and we don't have to rearrange anything. Now that you know how to solve using differentiation, you're ready for whatever life has to throw at you.